So in this section, we're going to be talking about the concept of hybrid atomic orbitals. So according to the valence bond theory, when two atoms overlap their atomic orbitals, the overlap that leads to the greatest area of the overlap is going to lead to the strongest bond. So there is a slight problem though. We know according to observation and also according to the VSEPR theory that we'll often see bond angles of 120 degrees or 109.5 degrees in molecules. But when we look at atomic orbitals that are overlapping to form these bonds with these particular angles, what we realize is that no atomic orbitals have these bond angles between them. So, there's no way for p orbitals to overlap in anything other than a 90-degree bond angle between them, because the set of three p orbitals are oriented along the x, y, and z axes. Similarly, if we look at the set of 5 d orbitals, we see that the angles between them, again, are 90 degrees. So how the heck are orbitals meant to overlap efficiently with bond angles of 120 degrees or 109.5 degrees? And we know these angles are observed in molecules, and you saw that in the lab. So a good example of this is to look at methane. And methane has tetrahedral geometry with bond angles, the perfect tetrahedral angle of 109.5 degrees. If we look at carbon, we can see that carbon is forming 4 bonds here. So every bond we would expect to have one half-filled orbital. And those half-filled orbitals should be at an angle of 109.5 degrees between the orbitals, right? In order for valence bond theory to work. Well, none of that makes sense, because carbon has only 2 unfilled orbital or partly filled orbitals. So how the heck is it going to form 4 bonds? So the other thing, of course, is that these 2 partly filled p orbitals are not at 109 degrees to each other. They're at 90 degrees to each other. So how is this going to work? How are we going to make this molecule using valence bond theory? It seems to be broken at the first attempt at using it. So Pauling said that what you need to do is you have to mix all of the valence orbitals together. So if you take carbon has a valence electron configuration 2s2, 2p2, and what you're going to do is there's one orbital that makes up the 2s subshell, 3 orbitals that makes up the 2p. If you mix all of these together mathematically, you'd end up with 4 new orbitals. You can see there's a total of 4 orbitals here. And he said because it's made of 1 part s and 3 parts p, he would call this sp3. Then you would end up with 4 singly occupied orbitals when you put the electrons in them. Well, the thing is that's really, really cool about this, so that gives us a right number of singly occupied orbitals. It also turns out when you do the math on this, those orbitals end up being oriented at 109.5 degrees from each other. So it works. So this gives rise to the idea of what we call hybrid orbitals. And in this case, we've got sp3 hybrids because they are 1 part s and 3 parts p. Now, how many orbitals do you get when you hybridize? Well, you just want to add the numbers together. So we've got 1s, and then we've got 3 p's. So that means we're going to get a set of 4 sp3 hybrids. So the number of orbitals that you're mixing is exactly equal to the number of hybrids that you get. So if we look at what is happening in methane now, we know that methane CH4, hydrogen has this 1s orbital that is partly filled. Okay, and now the unhybridized carbon has the valence electron configuration 2s2, 2p2, And what we're going to do is we're going to hybridize the carbon, and that gives us a set of 4 singly occupied sp3s, and each of them is going to overlap with 1 singly occupied 1s orbital on a hydrogen atom. And so there's our molecule, all right? The hydrogen 1s overlaps with the carbon's sp3, and what does that do? Well, it gives us a single bond between the carbon and each hydrogen, and that's classified as being a sigma bond because for 2 reasons. It's a single bond, but also because it involves an s orbital, we know that that is a sigma bond, and also the overlap gives us increased electron density along the bond axis, not above and below the bond axis. So that's what's going on there. That's how that works. And we've just seen an example of sp3 hybridization on carbon, which is actually a very common pattern of bonding for carbon. There are some other molecules that have sp3 hybridization, but the important thing is that if you have steric number equals 4, your central atom in your molecule is always going to be sp3 hybridized, because that's how we create a tetrahedral set of 4 orbitals. So you just remember that your the number of orbitals that you're mixing, which is you're mixing 1s orbital and 3p orbitals, however many orbitals you're mixing, that's going to be equal to your steric number. So keep that in mind. The two are related. Okay, so if I look at the Lewis structure for ammonia, we see that we've got 3 single bonds, right? And we've got a lone pair there. So I know that I need, for every hydrogen atom needs 1 singly occupied orbital. And then the nitrogen here, it's going to need 3 singly occupied orbitals. And somehow we're going to have to figure out where the lone pairs go. So let's see what happens. It's got steric number 4. We want to sp3 hybridize this. So here's the unhybridized nitrogen atom, has electron configuration or valence electron configuration 2s2, 2p3. We're going to sp3 hybridize it. So we end up with 4 equivalent sp3 hybrid orbitals. And then we have to put in the 5 valence electrons. So we go 1, 2, 3, 4. And then we come back and put our 5th electron in. So you see here we have this doubly occupied orbital. That can't be used for bonding. That's what your lone pair is. And then these 3 singly occupied orbitals, they're the ones that are going to be used to make the bonds, and they're going to be overlapping with 1s orbitals on the hydrogen atom. Remembering hydrogen's only got the 1 electron, so that's going to be singly occupied. So these guys overlap with the 1s on the hydrogen atom, and then the whole thing looks like this, right? So again, it's going to be sigma bonds because they're single bonds, and also you have increased in electron density along the bond axis, not above and below. And they also involve s orbitals, and that always means that you have a sigma bond. The lone pair in here is located in an sp3 hybrid orbital, and that's it. It works really, really nicely. Here's another example of a steric number equals 4 molecule. This is water, and we have to remember that the valence shell electron configuration for oxygen is 2s2, 2p4. It has 6 valence electrons. Because it has steric number equals 4, we know that the central number will be sp3 hybridized. So here's our unhybridized central oxygen atom, 2s2, 2p4. Now we're going to mix everything together and we're going to create a set of 4 equivalent Sp2 hybrids. Because these guys are like 3 parts P and 1 part S, they're going to lie higher in energy than the 2S and a little lower in energy than the 2P. So we have 6 valence electrons to put into our hybrid orbital. So we go 1, 2, 3, 4, 5, 6. So the doubly occupied orbitals represent your lone pairs. They can't be used for bonding. And then these 2 singly occupied orbitals, they're used for bonding. They're going to be overlapping with the 1s of the hydrogen atom. So that's what it looks like here. The hydrogen 1s that is singly occupied overlaps with an Sp2 hybrid on the oxygen, which is singly occupied. So you end up with 2 electrons like that in the overlap region. And the same for the other hydrogen atom. And then the other 2 Sp2 hybrids that are centered on the oxygen contain lone pairs. These are sigma bonds again because they involve s orbitals, and they're also sigma bonds because we can just see where the electron density is. It's along the line joining the center of the oxygen and the hydrogen atom, not above and below. So that's pretty kind of, straightforward. Can we extend it and have other types of hybridization? Well, if we go to steric number 3, we will have what we call Sp2 hybridization. So this means we're mixing one s orbital with two p orbitals. So if we take a carbon, if we look at a carbon molecule, a classic one that has steric number equals 3, this is called formaldehyde. And so carbon still has electron configuration 2s2, 2p2 with 4 valence electrons, so 2s2, 2p2. And now what we're going to do is we're going to sp2 hybridize it. So we're going to mix the s, but this time with only 2 of the p's. So that leaves us with 1, 2, 3 equivalent. So we're just going to mix these guys, right? 3 equivalent sp2 hybrids, but then we also have 1p, this guy here, that we don't hybridize, and that's what's sitting over there. So now I have to put 4 electrons in here, and so I go 1, 2, 3, 4. Okay, now I've got 4 singly occupied orbitals. Is that a good thing or a bad thing? My number of singly occupied orbitals should equal the number of bonds I want to make. So I've got 1, 2, 3, 4 bonds that I would like to make, and I've got 4 singly occupied orbitals. This is looking good. So how are these guys oriented? Well, sp2 hybrid orbitals are in a trigonal planar arrangement, and then the unhybridized p orbital that comes along with an sp2 hybridized central atom is at 90 degrees to the plane of that sp2 hybrid set. Okay, you can also do the same thing for an outer atom. So here's this oxygen atom. Remember, it has valence shell electron configuration 2s2, 2p4, and we want it to make, it's got 1, 2, 3 electron groups around it, so its steric number equals 3, and we want to be making 2 bonds, and we also want to have 2 lone pairs on our oxygen atom. So let's see if it works. So we recognize that our oxygen atom has steric number equals 3, and so therefore that means that we're going to sp2 hybridize. So I'm going to mix the 2s with 2 of the 2p's, and then I'm going to leave that guy alone. So I've got 1 unhybridized p orbital, and then I've got a set of 3 sp2 hybrids. So let's see now, I have to put in 6 electrons, 6 valence electrons for oxygen. So I go 1, 2, 3, 4, 5, 6. So it's looking good because I've got my 2 doubly occupied sp2s, so they're going to be my lone pairs. And then I've got one sp2 that only has one electron in it. And then I've got my one singly occupied and unhybridized p. And we don't really, the electron is spread across both these lobes, but let's just kind of say that it's, it's kind of spread over the whole p orbital, but I'm just going to put it up there for now. So 1, 2, 1, 2, 2 half-filled orbitals for making my bonds, and then 1, 2, 1, 2, 2 lone pairs. Everything looks great. So how does this come together to form the molecule formaldehyde? So there's formaldehyde. So the carbon and the oxygen have to come together. So we'll just focus our attention on that. And what's going to happen when the carbon and the oxygen come together is that these are all singly occupied on the carbon. Okay, they're all singly occupied, all these sp2. And then two of the sp2s on the oxygen have lone pairs in them, but one is singly occupied. So what happens is the sp2 on the carbon that's singly occupied overlaps with the sp2 on the oxygen that's singly occupied, and we get a bond there. And that's going to be a sigma type bond because it is end-on overlap of the orbitals. Now also you have to keep in mind that the p orbital, the unhybridized p orbital on the carbon, is also singly occupied, as is the unhybridized p orbital on the oxygen. So when these guys come together, there's going to be some interaction there as well, but that's going to be above and below the plane or the line joining the centers of two atoms, and that's going to be pi-type bonding. So that's how we make the connection between the carbon and the oxygen. So now we have these these singly occupied hybridized orbitals on the carbon, and they're going to be available to overlap with the singly occupied 1s orbitals of hydrogen, of these two hydrogen atoms. And so that's what's going to happen in here. The hydrogen 1s that's singly occupied will overlap with the sp2 hybrid on the carbon that is singly occupied, and that'll happen twice, and then you get the molecule. So you can see here that the double bond, and we mentioned this earlier, is composed of a sigma bond formed through the overlap of sp2 hybrid orbitals, and then a pi bond that's formed through the overlap of unhybridized p orbitals. So it's kind of interesting. There's a few things here. What you can see is that you can't rotate the bond between carbon and oxygen, because to do so would mean you'd have to break this overlap here, and that requires a lot of energy. So double bonds, you can't rotate around them. Okay, so yeah, here's the full kind of diagram for formaldehyde. Important thing to keep in mind is that a double bond always involves one sigma, which is that guy in there, and then one pi, which are these regions of electron density above and below the line joining the centers of the two atoms. Alright, so if you mix one s with three p's, you get a set of 4 sp hybrids. If you mix one s with two p's, you get a set of 3 sp2 hybrids. So are there any other combinations? And I guess the obvious one is you could mix an s and one p, and then I wonder what that would give you. Well, 1 and 1, that would be what we see for molecules that have steric number equals 2. So you would get a linear arrangement, right? So you would expect that sp hybrids would be in a linear arrangement. So let's see what our friend Linus Pauling tells us. So here's an example of where we have a carbon atom that has steric number equals 2. So we've got 1, 2 regions of electron density. In fact, we've got 2 of these carbon atoms in this molecule. This molecule is called acetylene. It's commonly used for welding because breaking this bond releases a huge amount of energy. In fact, so much energy you can use it to melt steel. So in this molecule, every carbon atom is sp hybridized. And we know that a triple bond is comprised of 2 pi bonds and 1 sigma bond. So we'll keep that in the back of our minds as we kind of look at how this molecule is assembled. So for the carbon, what do we want? We want to have 4 bonds. We want to be forming 4 bonds. So that means we're going to need 4 unpaired electrons after we do this sp hybridization. So carbon has the electron configuration, or the valence electron configuration, 2s2, 2p2, and now we're going to sp hybridize. So we're going to mix an s with 1 p, and then the remaining 2 p orbitals we're going to leave alone. So here they are. These are the unhybridized p orbitals, and then we've got sp, we've got 2 sp hybrids, and they're going to be in a linear arrangement. So now we have to put in 4 valence electrons. So we go 1, 2, 3, 4. And sure enough, we wanted to form 4 bonds. 1, 2, 3, 4. And we have our 4 half-filled orbitals. This is awesome. This is looking really good. So now we're going to have 2 of these carbon atoms are going to come together, and it's going to form a triple bond between the carbons. So the carbons are going to overlap 3 orbitals each to form their bond, right? Now, we also need to, then once we've got the bond formed between the 2 carbon atoms, form the bond between the carbon atom and the hydrogen atom. So what's that going to look like? So sp3 hybrid orbitals, there they are there. They're at 180 degrees to one another in a linear arrangement, right? It's the same as the linear arrangement saying that they've got 100 degrees. What about the 2 unhybridized p orbitals that are centered on each carbon? Well, those unhybridized p's are at 90 degrees to each other, but also at 90 degrees to the sp hybrid orbitals. So you've got a set of 3, you've got a set of these 3 lobes looking like they're along the x, y, and z axes at 90 degrees to each other. Okay, so let's have a look at what happens when we bring 2 carbon atoms together. So here's carbon 1, here's carbon 2. You want to remember that every sp is singly occupied. Okay, so when the 2 carbon atoms come together, you can see that the sp hybrids that are singly occupied on each of them are going to overlap, and that will form a sigma bond because it is end-on overlap between the orbitals. You can also see that the p orbitals, the unhybridized p orbitals, are going to overlap side-on, and that's going to form 1 pi bond between those guys, and then at 90 degrees to that, another pi bond between those guys. So that's very sort of difficult to see. You wouldn't be expected to draw that. And then now every carbon has this singly occupied sp left, which is ready to overlap with the hydrogen 1s. So it all kind of comes together like this. You get a sigma bond forming between the hydrogen and the carbon. The 1s on the carbon overlaps with the sp hybrid on the 1s on the hydrogen overlaps with the sp hybrid orbital on the carbon. And between the carbons, you've got overlap of half-filled sp hybrids, but then you've also got overlap between those 2 unhybridized p orbitals forming 2 pi bonds. So that triple bond ends up being 2 pi bonds and 1 sigma bond. And the pi bonds are formed through the p orbital overlap. And the sigma bond is formed through sp orbital overlap. Okay? And yeah, that's how it works. So just keep this in mind. A triple bond is always 1 sigma bond and 2 pi bonds. And a double bond is always 1 sigma bond and 1 pi bond. Okay. If we have an expanded valence shell, then we have steric numbers equal 5 or steric number equals 6. In order to be able to create hybrid orbitals for these expanded valence shells, we have to start incorporating d orbitals into our hybrids. So if I want to go out to steric number 5, I'm going to sp2 dehybridize my central atom. So you can see I've got 1s plus 3p plus 1d. If I add all of that together, I would get 5 hybrid orbitals. And sure enough, it turns out that they are in a trigonal bipyramidal arrangement, exactly the same as what we would expect for an atom with steric number equals 5. So how do we make that? Well, we were not going to see this until we get to the third row or higher of the periodic table. So a good example of an element in period 3 is phosphorus. Has electron configuration 3s2, 3p3 for its valence shell, but the 3d is actually empty. So that doesn't matter, we're just going to steal an empty orbital from there. So when we sp2 dehybridize, we steal one of these guys and we mix it in with one of those. And so what we end up with is a set of 5, because we've got 1s, 3p and 1d, 5 sp2 hybrids. And we had 5 valence electrons to begin with. So 1, 2, 3, 4, 5. We end up with 5 singly occupied sp2 hybrid orbitals, and each of these orbitals could overlap with the singly occupied orbital on another atom to form a bond. So here we have PCO5, and what's happening here is we've got our 5 singly occupied sp2 hybrids, and they can overlap with singly occupied orbitals on chlorine atoms to form this compound PCO5. So sp2 hybrid orbitals have a trigonal bipyramidal arrangement of these hybrid orbitals. When we have steric number equals 6, we're going to be mixing 1s with 3 p's and 2 d's in order to get up to 6. And this gives us an octahedral set of what we call sp2 hybrid orbitals. So if I take something like sulfur, which has valence electron configuration of 3s2, 3p4, if I mix all of the 3s and the 3p with 2 d's, I end up with an sp3d2 set of hybrid orbitals. They're all at the same energy. I have to put in 6 electrons in there, so 1, 2, 3, 4, 5, 6. So now I have a central atom that can go ahead and form 6 bonds to its outer atoms. So yeah, if I want to have an expanded valence shell, I have to start taking advantage of the d subshell to form my hybrid orbitals. Okay, so what does it look like putting it all together? Well, the key thing is that the steric number will tell you how your central atom is hybridized. And the number of orbitals that you're mixing is always going to be equal to your steric number. So really, you just need to kind of expand your VSEPR geometries table to include an additional column that has the hybridization of the central atom in there, and then you'll be able to get these questions correct. So I just recommend having this table open in another tab when you're doing your tests and quizzes and so forth. Okay, so there's some problems in the book that it would be really helpful if you went through before Wednesday, and during that Wednesday session at 12 o'clock, I'm going to be working through those with you guys.